Hello and welcome back. How do we find arc lengths for a parametric curve? And also, how do we find surface areas of revolution given a parametric curve? Well, recall that the approximate length of a piece of arc can be written as delta s equals the square root of delta x squared plus delta y squared. That was a little triangle that we made where delta x was one leg, delta y was the other leg, and delta s represented the hypotenuse of that little triangle. So this is just the Pythagorean theorem. So that delta s represented the length of an infinitesimal, of a very small piece of the arc. Now dividing and multiplying by delta t squared to introduce this parameterization into the picture, we get something like delta s equals the square root of quantity delta x squared over delta t squared plus delta y squared over delta t squared times then delta t squared. So all we're doing here is just multiplying and dividing by delta t squared inside of the radical. Then the delta x squared over delta t squared turns into delta x over delta t quantity squared. Same thing with the delta y over delta t quantity squared. And then the square root of the delta t squared can be just written as delta t. So we can rewrite delta s as the square root of delta x over delta t squared plus delta y over delta t squared times, on the outside, delta t. Taking the limit as this arc is cut into more and more pieces, we get a length of an infinitesimal piece of the arc, which we used ds to represent that, is, well, all the deltas will basically just turn into d's, and that's going to be the length of the infinitesimally small piece of arc. So ds will be the square root of dx dt squared plus dy dt squared, and then times dt. So that's the ds that we can then use in all of the formulas that we learned before for arc length, for surface area of revolution about the x-axis, for surface area of revolution about the y-axis. We can just fill in the ds that we have into for parametric equations into all of these formulas that we learned earlier. So putting it together, the rest of it just tries to connect everything and fill in those ds's. So we have that the arc length for a set of parametric equations, so that's x equals f of t and y equals g of t, from t equals a to t equals b, you can get by taking the integral from t equals a to t equals b of the square root of dx dt squared plus dy dt squared dt. So that's where we're just filling in. Normally it's the integral of ds. Well, ds is what we just talked about earlier. The only note is that as you go from t equals a to t equals b, the curve has to be traversed exactly once. Otherwise, you might be counting double for the arc length, right? You can imagine if you're going around a circle, if you just want to figure out how far it is around the circle, then you only want to go around the circle once. You don't want to travel it twice, because that's not going to be giving you what you want to know. Then for the surface areas of revolution, there are the two situations, one where you're revolving about the x-axis and one where you're revolving about the y-axis. The only difference between them is that when you're revolving about the x-axis, you're going to have 2 pi y inside of your integral, and when you're revolving about the y-axis, you'll have 2 pi x inside the integral. The ds's will be exactly the same for each of those. So it's kind of nice. You don't even really have to choose what your ds is going to be when you have a set of parametric equations. It's always going to be dx dt squared plus dy dt squared dt. Again, the note, as you go from t equals a to t equals b, the curve must be traversed exactly once. Thanks for watching, and see you next time.